Here we go. So we talked about how to find standard deviation. We talked about variance. Now we got to get into a little bit more of what this all means. Before we can do that, we were looking at standard deviation and we compared data sets where the variables were the same. It just happened to be a different set of circumstances, but we were talking about the same thing. Sometimes we want to compare different variables, okay? And comparing that standard deviation compared to another standard deviation, when the variables are actually different, you know, it's apples to oranges. So we have to find a way to simplify that so that we can compare them together. And what we come up with to do that is what's called the coefficient of variation. It's pretty straightforward. It's a way to sort of level the playing field so that when I'm comparing apples to oranges, I can still look and see how much more spread out the apples are compared to the oranges, even though they're apples and oranges, okay? It's not like one set of apples and a different set of apples. So here's how the coefficient variation works, all right? First of all, we're using this to compare lists of different variables, as I mentioned, and we use the coefficient of variation in this notation. You'll see this lowercase c and the bar, c bar. That is coefficient of variation. Here it goes. So, we express it as a percent. There is a sample version and a population version. So, when you look in the book, the formula that they give you is a little bit different than what I'm going to give you, because I know that you already know how to convert a decimal to a percent, which is why I put it there in purple. So it's just assumed that after you get your little decimal, you take it another step and turn it into a percent. So here's what it looks like. We're just taking the standard deviation and dividing it by the mean. That's all that it is. Okay? So over here, all the different symbolism has to do with whether or not it's sample or population. Remember, S is sample standard deviation. The X with the bar on it. This is not an equals. I know that looks sort of like an equal sign. This is the X with the bar over it. That means the sample mean. Standard deviation divided by sample mean. Okay? For population, sigma is the standard deviation. Mu is the, sigma is the population standard deviation. Mu is the population mean. Again, if in your notes in words you want to write standard deviation divided by mean, write that down, because that's all it is. Okay, that levels the playing field. Standard deviation divided by mean. Obviously, under the sample column, you have the sample symbolism. Under the population column, you have the population symbolism. Standard deviation divided by mean. Yes?
That's both. We're both
correct. The both standard deviation divided by mean. One is the sample standard deviation, sample mean. One is the population standard deviation and population mean. Okay? Let's look at an example. If you want to take a picture of this screen, you're welcome to. I know that's littleish. Here we go. So here are the two different variables that are being compared. Okay? We're looking at two things. The mean number of car sales. Okay? So how many cars got sold. And we're comparing it to the commissions that those salesmen make. You guys know what a commission is?
Money.
It is money. So usually what commission is a percentage-based thing. So in sales, when somebody sells something, they get a percentage of that sale that goes to them. A lot of jobs have what's called a base salary that is incentivized by commission. So they get their whatever their base is. It's sort of like a waiter or a waitress. They have a base hourly wage and then they make tips. Okay. In sales, they have a base salary and then they make commission based on their sales. Same kind of thing. Okay. So in this problem, we're comparing sales of cars to commissions, which are two different variables. Right? So in order to find the variations of the two, we're going to have a coefficient of variation for sales. We're going to have a coefficient of variation for commissions. So go ahead and calculate that. You have all the information you need because it's just standard deviation divided by mean. Express it as a percent. So go ahead and find those coefficients of variations for each of those variables. The whole point is we have two different variables. We have car sales and we have commissions. So trying to compare the standard deviations of both wouldn't make a lot of sense because the commissions aren't going to be anything near what the cost of a car is. So when you make money on your commissions, a percentage of thousands of dollars versus number of cars sold, we're talking about this is the apples and oranges thing. Like you sell 20 cars in a month, but you make $10,000 in commission. How do we compare 20 to 10,000? Right? There is no comparison. One's dollars, one's number of cars. So that's why we do this sort of normalization by dividing by the mean, and then we can compare them to each other. Okay? So, what it should look like. For sales, the coefficient of variation is 5 divided by 87 because the standard deviation is 5, the number of cars sold was 87. For commissions, the standard deviation was 773 divided by the mean, which is 5,225. Okay? When you divide those by the mean, see, because if I just compared the standard deviation, if I just compared 773 to 5, it would seem like there's nothing in common there, right? The standard deviation is 5 cars, but the standard deviation for commission is $773. We can normalize that and compare them by dividing them each by their means. Okay? So when I do that, I end up with the coefficient of variation for sales is 5.7%. Again, you have to convert that decimal to a percent. And then the commission is 14.8%. So here's what this means. Okay? Which variable is more variable? Commissions, it's higher, right? Which means comparing the two to each other, what that means is that the commissions are going to be more spread out as compared to the number of cars that were sold. That's all it means. The number of cars that were sold will be bunched closer together than the commissions. Okay? And that's all we have to say. Okay? The commissions are more variable than the sales. You could also say the sales are less variable than the commissions. Okay, you can flip it around too. But when it says compare the variations of the two,
That's what you have to write something.
that's when you're writing this. Compare the variations of the two. Either commissions are more variable than sales, or sales are less variable than commissions. Okay?
So we just found the coefficient of variation.
Correct. Coefficient of variation, standard deviation divided by mean. Okay?
That's pretty easy.
Yes. So this thing is a little bit harder. One, it's harder for you to say. Chebyshev's theorem. I'm fine with Chebyshev. It's actually Russian, and you don't say it Chebyshev. You would say it more Chebyshev. But it's okay. I don't care. I'm not going to get bent out of shape about how you say it.
Are you Russian?
Actually, yeah, I am.
Wow.
I mean, no, I'm American. I have Russian heritage. How about that? All right. Here's what the theorem says. Okay? Because again, our whole point is trying to figure out how spread out data is and where it is. Here's the theorem. You should write this down. So here's what this all means, okay? First of all, when we talk about a number of standard deviations away from the mean, okay? So once we calculate the standard deviation, one standard deviation away from the mean in either direction, so meaning I can add a standard deviation to get one standard deviation away, which would be bigger than the mean, or I can subtract one standard deviation to go one standard deviation less than the mean. So I create this range where I'm one standard deviation away from the mean, okay? Or two standard deviations. And each standard deviation changes for the standard deviation for that problem, okay? So what Chebyshev's theorem talks about is how much of the data lies within so many standard deviations, okay? And in this case, that so many standard deviations is k. So we talk about k standard deviations. A certain percentage of all the data will lie inside of so many standard deviations. Now, this formula tells us how to calculate what percentage of the data at least will fall within so many standard deviations. Now, important here that k does not have to be an integer. Okay, we talk about 1 standard deviation or 2 standard deviations. We could be 1.5 standard deviations away from the mean. We could be 3/4 of a standard deviation away from the mean. But the further I move away from the mean, the more of the data will be included. Okay, the smaller my standard deviation, the number of standard deviations that I choose, the less data will be there. Okay, and I'm going to show you a visual representation of all that here in a second. But let's go through a couple examples so you can kind of see what we're talking about here. Okay, so at least 75% of all the data will be in between 2 standard deviations of the mean. And I'm going to show you this by using that formula. So what I'm telling you here in this example is that k in this example is 2. The number of standard deviations away from the mean. Okay? Here's what this will kind of look like when we use the theorem. So k is equaling to 2 in this example. And so I plug 2 in for k. And I'm just going to simplify that expression, 1 minus 1 over 2 squared. So what is that? What is 1 minus 1 over 2 squared?
So it's 0.75, right?
Yeah, 0.75 or course, okay? Or 75%. So I just simplify that. When I have 2 standard, and this is true for any set of data, at least 75% of the data, so I'm talking about that entire list of numbers, whatever it is, 75% of those numbers, at least 75% of those numbers, will be within 2 standard deviations of the mean. Okay, so that means a quarter of the data will be outside of that. It's further away from the mean. Okay. Now, if I went out to 3 standard deviations away from the mean, I increase the number of data that will be included in those 3 standard deviations. So for 3,
Wait, why would you subtract it by 1/4?
because that's how the theorem works. 1 minus 1 over k squared. So in this first example, k was 2 standard deviations, 2 squared is 4. Now down here, if I go 3 standard deviations away from the mean, now we're going 1 minus 1/9, which is 8/9, which is 88.9%. So again, as I move further away from the mean, because adding an extra standard deviation, I'm including more of the data. And it's at least 88.9%. Okay? So it actually can be higher than that, but at minimum, it's going to be 88.9%, 3 standard deviations away. Like I said, I'm going to show you an illustration, a graphic representation of that. I think on the next slide. Nope, not quite yet. Actually, maybe I should do that now so you can get an idea. Let's do that. I'm going to move this slide over to here so you can kind of see what I'm talking about. Okay. The key thing here is Chebyshev's theorem applies to every data set, regardless of the shape. Okay, so I'm going to show you one here. Let's make it a little bit bigger. Okay, so here's what this means. So whatever our data is, this is just a random shape. It's not always going to look like this. This is just an example. Okay, notice here. Actually, don't take a picture yet because I'm going to put some more lines up there. So notice here. There you go. That red line indicates where the mean is. Okay, that's at the bottom there, it was that X bar. So what we're talking about is however many, in this case, standard deviations away from the mean. Okay, so you take the standard deviation times 2, add it and subtract it, And that's where these values come from. So that means 2 standard deviations away from the mean. Okay? And so what I'm trying to tell you with Chebyshev's theorem for 2 standard deviations away from the mean, and if you notice here, it lines up with this. So at least 75% of the data is going to fall between those 2 red lines because those are 2 standard deviations away, which means I'm excluding a bunch of data. Okay? So as soon as I start moving another standard deviation away, okay, and that's where we get into that 89%, okay, out here, so notice at the bottom it's x, or the mean, x with the bar on it, plus 3 standard deviations, and then on the other side minus 3 standard deviations. So I almost have all the data in between that area, okay? And that's what this theorem is talking about. How much of the data will fall within x or k number of standard deviations. Now let's look at a problem, okay?
Which we go ahead and take a photo.
So let's say the mean of a set of data is 65. I'm not giving you any context, let's just work through the numbers. And the standard deviations is 7. Okay? So that is enough information to tell me where most of the data will be. Because how far away is 2 standard deviations from the mean? How far is how 14, how did you get that?
7 plus 7.
7 plus 7, or 2 times 7, right? If 1 standard deviation is 7 away, 2 standard deviations is 14 away. 3 standard deviations is 21 away. Okay? That's all you've got to calculate there. So, 2 standard deviations above 65 is 79. Because that's just 2 times 7.
This is part of figuring out the answer, right?
I'm sorry?
This is part of figuring out the answer?
Yes. Okay? So I just add that, 65 plus 2 times 7, to get my sort of upper level. 2 standard deviations above is 79. So what's 2 standard deviations below? 51. What do you do? 65 minus 14. So I add 1, I subtract 1. So my 2 standard deviations below is 51. And now here's what that means. Okay? Since what we've said is that at least 75% of all the data in the set is included in between the 2 standard deviations. What this means about this data is that at least 75% of all of the data in the set are going to fall between 51 and 79. That's what it tells me. Okay? If I wanted to say 3 standard deviations, then I would add and subtract another 7, and then I could tell you that at least 88.9% of all the data is going to fall between 44 and 86. Okay? It's just the number of standard deviations. Yes?
So,
If you wanted to see 3 standard deviations, you could do that calculation. I just did this as an example. Okay? More likely the kind of problem you're going to see is going to look like this. Okay? I know that's really small. A survey of local companies found that the mean amount of travel allowance for executives was 25 cents per mile. Okay? So here's what that means. So people who travel for business oftentimes get reimbursed for their travel expenses. Okay? In this case, they found that the mean was 25 cents a mile. So people who travel for work have to keep track of how far they go, and then they get reimbursed.
as in cars?
Yep, cars, planes, whatever. Okay? This in this case it's probably by car or some type of vehicle. Okay? The standard deviation is 2 cents. So using Chebyshev's theorem, find the minimum percentage of data that will fall between 20 and 30 cents per mile. Now here's what's going on here. On the examples we had before, we calculated the number of standard deviations away. in this case, we have to find out K. We don't know how many standard deviations we're trying to figure out here. We know what the standard deviation is, but we don't know how many standard deviations away from the mean 20 cents and 30 cents is. So we have to do that calculation. And the reality is, okay, 25 cents, the mean, is right in the middle here, okay? Right, so you can tell pretty easily how far away the 20 cents and the 30 cents is from the mean, right? How far away is it?
5 cents.
5 cents away, okay? So,
Can you have half of a deviation?
Three.
yes.
Is that what this is?
Yes.
Guessing that?
Guessing what?
It's 0.251.
No, they tell us the mean is,
Yeah, that'll.
they tell us the mean is 25 cents, and they give us the range from 20 to 30. Okay? So, you can look at either, you can go either direction, right? I can take the upper value minus the mean. I can take the mean minus the lower value. I chose to take the upper value and the mean. So here's what that means. Here's what all that means. Okay, since in either direction it's 5 cents away, what we have to be able to calculate is how many standard deviations is 5 cents. Okay, if we know that the standard deviation is 2 cents, and in this case we're 5 cents away, how am I going to calculate the number of standard deviations that 5 cents is? Yeah. By? Exactly. So we're going to take that difference and we're going to divide it by the standard deviation. Okay, we're going to take that difference and divide it by the standard deviation. So here, this is the difference. And that's the standard deviation. Now, Bridget asked, can you have part of a standard deviation? And yeah, you can. You can have the decimal part of a standard deviation. Because obviously, if the standard deviation is 2 cents, each deviation is going to be at an increment of 2 cents. Well, 5 cents is not in an increment of 2 cents, right? It's not 4 cents or 6 cents or 8 cents. 5 cents is going to be a fraction of that. So that's why you do this division. And so how many standard deviations is 5 cents? 2.5. Okay, so there are 2.5. 5 cents is 2.5 standard deviations, which means 20 cents and 30 cents are 2.5 standard deviations away from the mean. Okay, now what we've really found is K. K equals 2.5, which means, because the question is, what's the minimum percentage of data values in that 20 to 30 cent range? So now once I have my K, I can plug that into Chebyshev's theorem, and you can tell me the minimum percentage. So do that. I have K, so just plug it into the theorem, and then turn it into a percent. And so we can say what percentage of all the data will fall between 20 and 30 cents. Okay? So 1 minus 1 over 2.5 squared. Again, K is 2.5.
Yeah.
You can put that all in your calculator. 84%. So what that means is the minimum percentage of data between 20 and 30 cents, minimum, it could be more, is 84% of the data is going to fall in there. So what that also means is that some companies pay less than 20 cents per mile for travel expenses. Okay? Some companies pay more than 30 cents per mile for travel expenses. Not most of them, though. Most of them are in the 20 to 30 cent range. But there are some that pay less, and there are some that pay more. And so that's a consideration when somebody accepts a job. Like, how much are you going to reimburse me? And if you reimburse me less, hopefully you're saying, okay, well, pay me more then. If I'm going to have to eat more of that cost, pay me more. Now, sometimes an incentive can be in a higher travel reimbursement, and then they lower your salary because they're paying you back more. And so we're covering more of those costs, which means you keep that money. Okay? We have a few more things to look at. Okay? as I mentioned before, and when I showed you that picture, Chebyshev's theorem works regardless of the shape of the distribution. The example that I showed you was just that, an example. Data can come in lots of different forms. It doesn't have to look like the histogram that I showed you. It can look different than that. All right. However, the number of data points, the percentage of data points, still remains the same regardless of the shape. There is a special type of shape that actually will have more data than you would have expected. Okay? The key thing with Chebyshev's theorem is we always say at least 75%, at least 84%, at least 88.9%. That means there can be more. When the data takes on a bell shape, okay, and we've talked about bell shape before, when it's a perfectly bell-shaped curve or display, oftentimes that's called a normal display, so you get used to that. It makes up what's called the empirical rule. And with the empirical rule, we gain even more knowledge about how much data is where. You've maybe heard the phrase a normal distribution or a norm reference test. You know, the SATs and the ACTs are norm reference tests. Okay? What that means is they force the data to look a certain way, meaning they want so much percent of the data to fall within one standard deviation, so much percent of the data to fall within two standard deviations, etc. Okay? And what I'm about to put up is how the empirical rule works and what a normal distribution is supposed to look like. So here it is. Okay? So before we were talking about 2 standard deviations, 3 standard deviations, we weren't talking about 1 standard deviation. K has to be greater than 1 in Chebyshev's theorem, because if it equals 1, then it makes it seem like it doesn't work. Then it makes it seem like 100% of the data, or sorry, 0% of the data falls within 1 standard deviation, because you have 1 minus 1. That's why we don't use Chebyshev's theorem for 1 standard deviation. It has to be greater than 1. But what this is saying is that in a norm reference situation, in a bell-shaped curve, for the empirical rule, okay, what will actually happen when it's distributed this way is about 68% of the data will be within 1 standard deviation of the mean. And then 95% of all the data will be within 2 standard deviations. So before we said at least 75%. Well, if it's shaped like a bell, it jumps from at least 75% to 95%. Okay? And then 99.7% of the data falls within 3 standard deviations. I'm going to show you 2 graphs. And you can take pictures of both, but I want you to kind of see what I'm talking about. Alright, so the first one, okay, the histogram version, and I'll draw those lines on there again. So 68% of the data within 1 standard deviation. 1 standard, and so notice at the bottom you see the mean minus 1s. That means x minus 1 standard deviation. I'm sorry, mean minus 1 standard deviation. Mean plus 1 standard deviation. Okay? Then, for 2 standard deviations, when it's shaped like a bell, and I'm going to show you the bell shape here in a second. Okay, so notice how that lines up. Nope. So 2 standard deviations now, we increase to 95% of the data. 95% of all the data is now within 2 standard deviations of the mean when it's shaped like a bell, when the empirical rule applies. So, in case you're not quite seeing the bell, here's another version of the exact same thing in a curve. Okay? So here's what's going on here. Okay, again, 68% of the data falls in between one standard deviation below and one standard deviation above. Okay. 95% of all the data is within 2 standard deviations of the mean. Again, that's what these bottom ones mean. Minus 1 standard deviation, minus 2 standard deviations, minus 3, and greater than 1 or 1 standard deviation above, 2 standard deviations above, 3 standard deviations above. It doesn't necessarily tell us what the data is, it just tells us how much of the data falls where. Yeah.
So this is only for the perfect bell-shaped one?
Correct.
The other ones would
Correct.
be not perfect.
Correct. So when it is a norm reference thing, when the empirical rule applies, when the data is distributed like a bell, okay, it's going to have so much, I can tell you much better in terms of the percent. Instead of saying at least 75%, I can tell you that 95% of the data is going to be in between those 2 standard deviations, okay?